Hey, Nithya. So we're looking at number 6 and 7 and 8. Your work on number 6 looks perfect. Number 7, actually, if we think about this trough filled up to height h, your expression for what the volume would be at that point is not quite right. So let me show you the work I did on this. All right, so let's look at this. If we have this trough filled to height h, let me get a good line here. So I drew an end view of this trough filled to height h, and we're going to come up with the area for that end piece, and then of course multiply it by 10 to get the volume. But if we have this equilateral triangle filled to height h, then this height h is the middle side of a 30, 60, 90 triangle. We divide by square root of 3 to get the short side. So this short side is h over the square root of 3. And of course, over on the other side, it's also h over the square root of 3. So the base of the triangle is 2h divided by the square root of 3. So the area of that triangle is, in fact, 1/2 the base times the height, 1/2 2h over the square root of 3 times the height, which is h. So the area of that triangle, when it's filled to height h, is h squared over the square root of 3. So the volume of the trough filled to the height h is 10 times that. 10h squared over the square root of 3. And so that's what the expression for volume ought to be over here. I left that square root of 3 in the denominator because we don't have to rationalize the denominator until we get our final answer. It doesn't matter how we carry it through the calculation. But the volume is actually 10h squared divided by the square root of 3. And then you can proceed to do dV/dt and figure out the answer to the question. Okay? So let's look at number 8. Now, there's a problem with the way they state number 8. It doesn't make any sense as stated. I actually looked up this question online because it didn't really make any sense to me the way this was stated. It should be, find the volume of the balloon at the instant when the rate of change of the surface area, rate of change of surface area is equal to 6 times the rate of increase of the radius of the sphere. The reason this problem wasn't making any sense to me is they don't tell you anything about the rate that the balloon is being inflated. And if the balloon was being inflated very fast, which means the radius was increasing very fast, then 6 times very fast would be a big surface area and it would be a big volume. However, if the rate was very slow, very, very slow, then 6 times a very slow rate would also be a very small surface area, and the volume would be very small. So this doesn't make any sense as stated because you couldn't get a definitive answer. It would depend on the rate that the balloon is being inflated, which they don't tell you. So when I looked this up online, this exact wording came out, except it says rate of change of surface area. Now the problem makes sense. So you wrote down surface area equals 6 times the RDT, which is right from what they told you. But I'm adding in d dt of surface area. The rate of change of surface area equals 6 dr dt. And we can get the derivative with respect to time of surface area by taking derivative of that which is 8 pi r, dr dt. So let me go back to a bigger view of this. Okay, so we have 6 dr dt equals 8 pi r dr dt. So 8 pi r equals 6. R equals 6 over 8 pi, which is 3 over 4 pi. And so we can plug that radius into the equation for volume to get the volume equals, you can check the way I did all this, but I plugged 3 over 4 pi in for radius into the formula for volume of a sphere. And I think I reduced it all correctly. You can check that. We end up with volume equals 9 over 16 pi squared. Anyhow, that is a way to do this problem that hasn't made sense. You have to add in the words when the rate of change of surface area is 6 times the rate of increase of the radius. Actually, when the rate of increase of the surface area is 6 times the rate of increase of the radius of the sphere. Then you're having two rates that are related to each other, and we can make sense out of that. I've stated it not only doesn't make sense, but it doesn't agree with similar problems that I found on the internet, which all refer to the rate of change of surface area. Okay, so I hope that makes some sense. I suggest you do this problem that way, because it is a way to get to a definitive answer, and really, as stated, there can be no definitive answer, because if you propose a really fast rate of balloon filling up, you'd end up with a different answer as if you propose a really slow rate of the balloon filling up. And since they don't tell you anything about the rate of the balloon being filled up, that means it must not matter, but in fact it does matter. You can't get a definitive answer unless you pin something down about the rate of change of something. Okay, I hope that makes sense. I'll get this over to you. See you later.